All right, so this is chapter 2, lesson 2. We're going to look at derivatives of polynomial functions. So yesterday we started looking at derivatives and saying the derivative function was the limit of our difference quotient. Today we're going to see if there's any patterns with this. So we have this little investigation, and you can see there's a pattern to my investigation. We're going to find a derivative using first principles, meaning using the limit of the difference quotient of 5, and then x squared, x cubed, x to the 4, and so on, and so on, and so on. So let's go over some of these. So 5 isn't too bad at all. If you want to think of it this way, instead of thinking of it as 5, you can think of it as 5 times x to the power of 0, because x to the power of 0 is just 1, and that sort of follows with the pattern that I'm trying to do here. All right, so for a, f prime of x, or a derivative of x, is going to equal the limit as h approaches 0 of 5 times x plus h to the power of 0 minus 5 times x to the power of 0 all over h. So what I have here is just both of these to the power of 0 is just 1. So I have 5 minus 5, which is 0 over h, which is just 0. So I'm trying to find the limit of 0. Well, that's just 0. So our first one here is just going to be, let's write this in here so we can see the pattern later. It's just going to be 0. All right, so let's try the second one. F prime at x is the limit as h approaches 0 for x plus h minus x all over h. Well, x minus x is going to go. Then I have h over h, which is just 1. So I'm trying to find the limit of 1. That's just 1. Okay. All right. So this one is just going to be 1. I wonder if the next one's going to be 2. Well, the next one we did yesterday. All right, so if you remember this, we did x squared all in yesterday's lesson, and the derivative was 2x. Okay. I don't know why I wrote 2 here when I said 1. There we go. So let's look at D then. So we have 0, 1, 2x. What about x cubed? All right. So f prime at x then will be the limit as h approaches 0 of x plus h cubed minus x cubed all over h. You can expand this out. You can do it the long way, or if you remember Pascal's triangle, you can do it that way, which is like this. 2, 1, 1, 3, 3, 1. So that's x to the 0, 1, 2, 3. So that last row is what we care about. So this will equal the limit as h approaches 0 of what we have, x cubed plus 3x squared h plus 3xh squared plus h cubed, okay, and then minus another x cubed here, all over h. All right, so that x cubed is going to go with this one. And then with our remaining terms, we can factor out an h. So we have the limit as h approaches 0 of h times by 3x squared plus 3xh plus h squared all over h. So the h's cancel, and now as we assign h equal to 0, these last two terms are going to cancel, and we're just left with this first term, 3x squared. All right, so going back over here, this derivative then is 3x squared. you might be able to start to see a pattern here. We can do the same thing for the last example, which is x to the 4. I'm going to do it over here. So x to the 4 would be the limit as h approaches 0 for x plus h to the power of 4 minus x to the power of 4 all over h. All right, so x plus h to the power of 4. Let's just go back to Pascal's triangle and do the next row. So it's going to be 1, 4, 6, 4, 1. Okay, let's do that. So this equals the limit as h approaches 0 of x to the 4 plus 4x cubed h plus 6 x squared h squared plus 4xh cubed plus h to the 4. And then finally minus this last term, x to the 4, all over h. So x to the 4's cancel. I will pull out an h. So we get the limit as h approaches 0. So factor out an h, and we're left with 4x cubed plus 6x squared h plus 4xh squared plus h cubed all over h. So our h's cancel. And as we set h equal to 0, these last three terms are gone, and we are simply left with 4x cubed. So this derivative is going to be 4x cubed. So now look at our pattern. This is quite amazing. So if we have just a constant, the derivative of a constant is 0. And you can prove that the derivative of any constant is 0. This we call the constant function rule. So if f at x equals k, where k is a constant, then the derivative will simply equal 0. Now the next four sort of show what we call the power rule. So think of this as x to the power of 1. Well, we got a coefficient of 1 in front. What about this? This is x to the power of 2. And then we had a coefficient of 2 in front. This is interesting. X to the power of 3 with a coefficient of 3. X to the power of 4 with a coefficient of 4. Wow. So that power simply became the coefficient that you put in front. Okay, what about the actual x? X to the 1 just became x. X squared became, x to the 1 became nothing. X to the 0 if you want to think of it. 1x to the 0. X squared became x. X cubed became x squared. X to the 4 became x cubed. So it looks like the power of x was just reduced by 1. And so this leads us to the power rule. The power rule says if you have anything x to the n, the derivative is simply, okay, we'll bring that n and make it the coefficient, so multiply by n, and then subtract 1 from the exponent, and that's your derivative. And we can prove this down below. So let's prove it using first principles. Let's say we have x to the n. So with first principles, we will then have the limit as h approaches 0 of x plus a little bit of h to the power of n minus x to the n all over h. Okay, so this we have to expand. Okay, and we can expand this with this property right here. So we write it as a minus b, where a is x plus h, minus b, where b is x. So we get x plus h minus x, so the x's can just cancel. And then we're left with all of this. X plus h to the n minus 1 plus x plus h to the n minus 2 times x plus x plus h to the n minus 3 times x squared plus x plus h to the n minus 4 times x cubed, and so on and so on and so on for whatever value of n you have up to. All right, well, if these two x's cancel, we're left with just an h in front, which can cancel with the h in our denominator. And so now we're left with this huge expansion. But as we set h equal to 0, every term just becomes x. So here we have x to the n minus 1. Here we have x to the n minus 2, but then multiplied by x gives us x to the n minus 1 when you add that one exponent to it. Then you have x to the n minus 3 multiplied by x squared gives us again x to the n minus 1, and then again x to the n minus 1. So you have n terms of x to the n minus 1. So you can just write that as n terms times x to the n minus 1, which is your power rule. Right? So guess what? You don't have to do limits anymore. All you have to do, for now, I'm going to teach you many different rules for taking derivatives, but we're going to start with this power rule. And we can expand the power rule a little bit. So let's say we have some function where the function is some constant times our power rules. So times some x to the power of n, or times any other function. Right? We can simply say the derivative of that function is just that constant multiplied by derivative of this function. So having a constant out in front isn't a big deal. You just multiply your derivative by that constant. All right, well, what about the sum rule? Let's say we have two functions, p and q. Well, the derivative then of the sum of p and q would just be the sum of their derivatives respectively. And the same with the difference. If you find the difference between p and q, the derivative of those differences is just the derivative of each, is just the difference of each derivative separately. And so we're going to practice with these rules. I've written them here all in Lagrangian notation, but over here, if you're curious, which we will use sometimes, I've written it in Leibniz notation. So this can make things a lot easier. So question 3 says, let's use this pattern to find the derivative of this function, x to the 39. Now, if you had to do that with limits, good luck to you. But all we're going to do is say the derivative of this function is, okay, multiply by 39. So bring that 39 out front. And then subtract the exponent by 1. There you go. You're done. So first example. Here we're going to just find the derivative of these functions. So let's do part A. So we have a function 7x cubed. So the derivative then is just going to be, well, take the 3, multiply it in front, right? The 7 is still going to be there, right? So 7 times 3, and then times x, and reduce the exponent by 1. So 3 minus 1 is 2. 7 times 3 is 21, so the derivative is 21x squared. Yes, it is that easy. No more limits for us. All right. So next, find the derivative of this one. We'll multiply by the exponent, which is 4/3. So we still have that 12 there, times 4/3 times x, and subtract the exponent by 1. So 4/3 minus 1 is 1/3. Right, so 12 divided by 3 is 4, times 4 is 16, so 16x to the 1/3. Okay, so example number 2 then. Let's do part A. So to find the derivative of this function, let me rewrite this function, because this is the square root of x. I haven't really told you what the derivative of the square root of x is, but remember, you can think of the square root of x as simply x to the power of 1/2. So write it as an exponent instead, and then we can work with it. Right, so here, derivative of 3x squared, so 2 times 3 is 6. Reduce the exponent by 1, so we just get x. Over here, you'll have 5 times 1/2, multiply by the exponent, and then subtract the exponent by 1, so you'll have x to the minus 1/2. And then we're going to clean this up a bit. So we have 6x minus 5 over 2 root x. So there's the derivative for that one. Okay, for part B, later on, I will teach you an easier way of doing this one. But for now, we're simply going to expand it first. So if we expand that, it's a nice perfect square there. We are going to get 9x squared plus 12x plus 4. So that's just expanding that. And notice I'm writing y instead of f at x. So using Leibniz notation, the derivative, dy by dx. Okay, do one at a time. We're going to use the sum rule. So 9 times 2 is 18. Times x, subtract 1, so just x. And this one is just, well, times 12 by 1, which is just 12. And then x, 1 minus 0, x to the 0 is just 1. And then any constant is 0. So there's your derivative for part B. So this last example says, determine the equation of the tangent to the graph of f at x. So yesterday when we did this, we did a question very similar to this, but we did it with limits. And a lot of you are wondering, why can't we just find the limit for f at 1? Why do we have to find the limit for an arbitrary x first? And this is why. Because now I've taught you a much easier way of doing it. So let's find the derivative for the function. So 3, so multiply by 3, so we get minus 3x. Subtract the exponent by 1, so 3 minus 1 is 2. Plus, okay, so 2 times 3 is 6. Times x, subtract the exponent by 1, so 2 minus 1 is just 1. And then any constant is 0. So here's your derivative. Now if you want to find then the slope of this function at 1, find the value of that derivative at 1. So we get minus 3 times 1 squared, which is 1, plus 6 times 1, which is just 6. So we end up with 3. So the slope at the position 1 is 3. Really easy, isn't it? But now we have to find an equation for this tangent. So we don't just need the slope, we need a point for where this tangent goes through to find the equation of a line. So to do that, well, we know the x-coordinate is 1, so let's figure out what the function equals at 1. Right, so we're going to substitute 1 into our function, so we're going to get minus 1 cubed plus 3 times 1 squared minus 2. So here we get 3, minus 2, minus 1, so that's just 0. So now we have a point, right? The point is 1 and 0, and we have a slope. The slope is equal to 3. So now we can use our slope equation. Right? If you remember, m equals y minus y naught over x minus x naught. Right? Where m is the slope, and y naught and x naught is our known coordinate for something on the line. So this is going to be 3 equals y minus 0 all over x minus 1. Rearranging, you just get y equals to 3 times x minus 1, or y equals 3x minus 3. So there's the equation of your tangent. All right, so the next part says determine points on the graph in example 3 where the tangents are horizontal. Now this is going to be extremely important. I said make sure you remember what a derivative means. We got the derivative function by taking the limit of the difference quotient, and the reason we did that was to find the slope of the tangent at a point on the function. And this will eventually help us graph the function. And this right here, this question is sort of a lead-in to that later on. This could tell us where on the graph the slope becomes 0. So where on a graph does the slope become 0? Let me give you some examples. If you have a graph that looks like this, the slope becomes 0 there. If you have a graph that looks like this, the slope becomes 0 here. Right? And you can have other cases, which we'll go over later. But finding where you have a horizontal tangent can be very, very important. So how are we going to do this? Well, we know the function, and we know the derivative of the function. Derivative of this function we solved up above is minus 3x squared plus 6x. Now remember what the derivative means. It's equal to the slope of the tangents. So if we want to know where we have a horizontal tangent, we want to know where this slope equals 0. So for what values of x? Now be careful, you might feel like you want to just cross out an x there, but you can't divide by x, because it is possible that x equals 0 is a solution. So what we're going to do is factor out an x, and it looks like we can factor out a -3 there too. Right, so find a factor. So we have -3 of x, that's going to give us x, and then -3. So that is all going to equal 0. Not 3, sorry, 2. There we go. So 3 times 2 is 6. There we go, that's much better. So this gives us two possible solutions for x. So x can be 0, right there. If x is 0, that equation is true. And x can be 2. Right? So if x is 2, 2 minus 2 is 0, that equation is true. So for this function, there are two locations where we have a horizontal tangent, where x equals 0 and where x equals 2.